Quicksort is another common sorting algorithm, and it's actually very similar to merge sort. The idea is that instead of splitting the array into two equal halves and then sorting those halves, instead, we're going to pick a random value, and for convenience, we usually pick the rightmost value, and this is called the pivot value. So the pivot value is special because what we're going to do is we're going to iterate through every single value in the input array except for the pivot value, so basically every value before the pivot value, and we're going to compare that value to the pivot. And every value that's less than or equal to the pivot value is going to be in the left partition of the array. So what we're going to do is take the input and partition it into two pieces, a left and right piece, where every value that's less than the pivot, less than or equal to the pivot, is going to go in the left half, and every value that's greater than the pivot is going to go in the right side. And performing this partition is actually pretty simple in terms of code. And we can actually perform the partition in place. That means we don't need to allocate any extra memory to do the partition. We can do it with just a single array. What we're going to do is take the rightmost value. That's going to be called our pivot. We're going to have a pointer that's going to start at the beginning of the array. And the idea is, if we took every value that's less than or equal to the 3 and then placed them in this leftmost area, if every value in the input array that's less than or equal to 3 was placed over here, then by definition, all the values that are greater than 3 would take up the remaining spots. As long as we swap them appropriately, that's going to be the case. So all we have to worry about is taking the values less than or equal to this and then filling them starting at the left side. If we do that correctly, then the less than or equal to values will be here and the greater values will be here. So let's start doing that. So we're actually going to have two pointers. One pointer is just going to help us iterate through here, and then the second pointer is going to tell us where we should insert the next value that is less than or equal to 3. So first we get to 6. 6 is not less than or equal to 3. So in this case, we don't do anything. We take our pointer over here and then shift it to the right by 1. This pointer stays here because when we do find a value less than or equal to 3, this is the first spot we're going to put it. So now we find a 2. 2 is less than or equal to 3. So we swap 2 with whatever happens to be in this position. So we can swap these two values. 6 goes here and then 2 goes here. Now this pointer that's over here is going to be shifted over here. Now this is the next spot that we're going to insert the value that's less than or equal to 3. So next we can take this pointer and then increment it one more time. So now we're at 4. Is 4 less than or equal to 3? It's not, so we don't do anything with it. We increment our pointer one more time. We get to 1. 1 is less than or equal to 3. So that means this 1 is going to be placed where this pointer happens to be. So we'll be swapping these two, placing the 1 over here, and placing the 6 over here. And then this pointer will finally reach the pivot index, and we don't really need to do anything. We basically ignore that. But at this point, our array looks something like this: 2, 1, 4, 6, 3. We wanted to partition the array such that every value less than or equal to this was on the left side, every value greater than this was on the right side. But where should we actually put this pivot itself to satisfy that? Well, this is where our pointer ended. That means our pointer is here. That means every value to the left of that is less than or equal to 3. So this is a good position to put our pivot at. So that's exactly what we're going to do with Quicksort. We perform one last swap between where our left pointer is at and our pivot value. So we end with a 3 over here and a 4 in this position. So to make it more clean, after doing our partition, we have a 2, a 1, and a 3 over here, and we have a 6 and a 4 on the right partition. Now notice how the left side is not sorted and the right side isn't sorted. Just because we partitioned them does not mean they're sorted, but what is true is every value on the left is less than every value on the right. Every value on the right is greater than every value on the left. Now this is where the recursive step comes in. Now let's run quicksort on the left side and run quicksort on the right side. Now before we recursively run quicksort here and here, one thing to notice about the 3 is that it's already in sorted order. Everything to the left of it is less than or equal to it, and everything to the right of it is greater than or equal to it. So this 3 doesn't actually need to be part of our equation anymore. We can just ignore this. So it does exist, but we're not focusing on it. When we run quicksort on this subproblem, let's just focus on these two values. This is already exactly where it needs to be. And that's always going to be true of the pivot value. So now we're going to choose the rightmost element, which is going to be our pivot. So in this case, 1 is our pivot. We're going to start at the beginning of the array. We're going to compare 2 to the pivot value. Is 2 less than or equal to 1? It's not. So we don't do anything. And then we would take our pointer increment to be here. It's at the pivot, so we don't do anything. That's when we stop. And the last thing we do before we split the array is we take the pivot and swap it with wherever our left pointer would have been. Remember, our left pointer starts here, and since we didn't end up swapping anything here, our left pointer would stay here. So what we're going to do is take 1 and 2 and then swap them. Because we know our pivot should go at the beginning, 1 should go at the beginning, 2 should be here. And so this is the index that our pivot went to. And I didn't mention this earlier, but when we take the array and then split it into 2 pieces, we do it based on where the pivot value was inserted. So the pivot value 3 was inserted right into the middle. That's why we took the first 3 values and then put them over here, even though we didn't actually include the last value. And then we took all values to the right of that pivot and then, ran quicksort on them over here. But so now that our pivot was over here, we're going to take the 1 and it will go on the right side, and then all the remaining values, in this case 2, are going to go here, and that's essentially the base case anyway. So when we run quicksort on this and this, we're not going to do anything. Of course, an individual element is already sorted. And remember, for quicksort, we're not allocating any extra memory. These swaps that we're doing are happening in place. That's the advantage of quicksort over a merge sort. We don't actually have to allocate extra arrays. Now, running quicksort on these 2 elements, this is going to be our pivot. This is where our pointer is going to start, and this is also where our left pointer is going to be the pointer that tells us where to insert the next element that's less than or equal to the pivot. So is 6 less than or equal to the pivot? Nope. So we take our pointer, our left pointer will stay here, but our I pointer will be incremented over here. And that's how you know we can stop when we reach the pivot. And then the pivot will always go to the position that the left pointer stopped at. It was over here, so we swap these 2 values. So this would be a 4, and then this would be a 6, and then we would run quicksort on these 2 subproblems, 4 and 6, but this is the base case. This is also the base case, so we're done. Now remember, this is happening in place. These are not extra arrays. So if this is in the first position, this is in the second position, we know that 3 was in the third position, right? And that was always going to stay there. This is in the fourth and this is in the fifth. We have a sorted array. Now, based on this example, the time complexity looks very similar to merge sort because we're breaking it up roughly into equal halves. But the thing about the pivot is we're always picking the rightmost value, and it might not result in equal halves. So if the elements were arranged a bit differently, in this case, they're already in sorted order, we would have 6 be our pivot. And what we would end up doing is partitioning every value less than or equal to 6 on the left side. All of these values are less than or equal to 6. So in that case, we would split this into 2 subproblems where we have the first 4 values over here, 1, 2, 3, 4, And then on the right side, we would just have 6. And then this 4 would be the pivot when we're running this subproblem, which would, keep the values in the same exact order. All these are less than or equal to 4. So then this would end up splitting it into something like this, 1, 2, 3, and then 4 would be over here. And we would essentially continue doing this until we complete it, which would look like this, 1, 2, 3. And then lastly, we would split this into 1 and 2, the individual values. But then this, all of a sudden, the height of this becomes n, where previously if we split it into equal halves, we know then the height of it is going to be log n. But in this case, we're not splitting it into equal halves. So in the worst case, the height of this is going to be big O of n. Now for each level, we're still having to iterate through approximately the size of the entire input. That's approximately how many we're going to have on each level. So in that case, the overall time complexity becomes n squared in the worst case. So that kind of shows us that quicksort is not necessarily better than merge sort. But on average, this is not going to happen. This is the worst possible case where the input is already sorted. One way to get around this is not to pick the pivot as the rightmost element. It's to take, maybe the leftmost value, the rightmost value, and the middle value. And among those three, choose the middle value and then use that as the pivot. So the way we've been selecting our pivot is a bit naive, but there are optimizations you can do which will help us to make sure that we don't hit this worst possible case. So on average, if we do split if we split the array into two roughly equal halves, then the time complexity of this obviously is going to be very similar to merge sort. In fact, the height is going to be log n, and since we know each step we're doing an O of n operation, then the overall time complexity for quicksort on average is going to be log n, not n squared. But the worst case still is going to be overall n squared. So quicksort is a pretty interesting algorithm. So the code for the partition would look something like this. Of course, the algorithm quicksort is recursive just like merge sort because we're splitting it up into subproblems. The base case is the same as merge sort. If the length of the subarray is less than or equal to 1, then the array is already sorted, we can return. Otherwise, we're gonna pick our pivot. In this case, we're doing it the naive way where we're just taking the rightmost element. We're also initializing our left pointer to S, which is the start of the array. And that left pointer is basically what's gonna tell us where we should insert the next value that's less than or equal to the pivot. So now to actually run the partition, we have a single pointer I, that's that pointer I've been referring to on the bottom, just scanning through the input. And we check, is this value less than or equal to the pivot? That's what we're checking here. If it is, we're gonna perform a swap. If it's not, we don't do anything. In this case, it's not less than or equal to the pivot. We don't do anything. We increment our pointer to be over here. Is this less than or equal to the pivot? Yes, it is. So let's perform a swap. First, we take the left value over here, put it into a temporary variable because we're about to overwrite it right now. We're going to replace it with the value at index I. This is that value. We're going to put 2 over here. And then we're going to replace this value with that temp value that we stored. So we're going to put 6 over here. And then lastly, we're going to increment our left pointer. So this pointer is now going to be incremented to be here. This is the next spot that we would insert a value that's less than or equal to the pivot, which is 3. So in general, this is how the partition is going to work. And don't forget, the last part of the partition is to take that pivot value and swap it with whatever happens to be at the left index. So in this problem, for this example, I'm pretty sure this is where we ended up swapping it with. And this is really the difficult part of the work. After that, the last thing would be the recursive step where we run quicksort on the left portion. We're taking left -1 because we know at left is the index where we put our pivot, and we know that the pivot is essentially in the perfect spot. In this case, 3 would be here, 4 would be here. The pivot is already exactly where it needs to be, so we're running quicksort on this half and running quicksort on this half. We're not even including the pivot value anymore. So we would do the left side and do the right side, and then we would return. So in this case, you can see the recursive step is pretty simple. The partition is where most of the logic happens to be. So the last question, is quicksort stable? And the answer is, generally speaking, no. There is a way to technically modify it so that it is, but generally speaking, quicksort is not considered a stable sorting algorithm, and let me show you why. The easiest way to do so is through an example. So we're going to partition this array. 5 is going to be our pivot. So we're going to be iterating through the array. 7 is not less than 5. 3 is less than 5, so we swap these two values. So now the 3 goes before the 7. We'll look at this value, it's not less than or equal to 5, and next we'll look at this, 4 is less than or equal to 5, so this is going to get swapped in the next position, which is over here. And you can probably see where I'm going with this. So swap these. So now our 3 is here, our 4 is here, and we have a couple 7s over here. I mean, the partition worked perfectly, but you can see that the original relative order of the 7s, the red 7 was here and the yellow 7 was over here. But now the yellow 7 goes before the red 7. So this definitely does not preserve the relative order of values when there's a tie between them. So generally speaking, quicksort is not stable. So adding to our list, we have quicksort, which is an unstable algorithm. Generally speaking, it is better than insertion sort, though the worst case time complexity, as I showed earlier, is n squared. The average time complexity is n log n. I know usually we care about the big O time, which is the worst case time. So if we're being super technical, it would be n squared, but generally speaking, people consider quicksort to be an efficient algorithm. On average, it's n log n. So that's how I'm going to list this as, but in a real interview, it would be worth mentioning that the worst case is n squared, but generally it runs more efficiently than that.